Yeah, so I was asked to say a few words on how I got into mathematics. And I thought about this for a bit, and I think actually the best place to start is with Abel. So when I'm Norwegian, I grew up here near Oslo. So when you're growing up in Norway, you hear about Abel like all the time, like this like young genius who made math discoveries in his teens. And in particular, you hear about this problem that the fifth degree equation cannot be solved. That's something that every 15-year-old hears. But when you're 15 and you know a little bit of math, you hear that, and your reaction is really, "Oh yeah, we'll see about that." And that was my reaction. So I literally tried to spend months trying to disprove Abel by proving that that you can solve quintic equations. Of course, I did not succeed in this. And when I started high school, I had a pretty good math teacher who gave me a book on Galois theory. And he saw that I was wasting my time doing this. And I basically spent the whole winter reading that book cover to cover. And at the end, I saw that Abel was right. you cannot solve the quintic equation. So that was great. I learned what the situation was, but still at that point, I felt that there was something that was a little bit unsettled, because I realized that there's sort of a difference between knowing the truth, or what the true statement is, and what you can sort of really understand. Like, I didn't really feel like I understood why the quintic was insoluble. Like, there's some proofs that you really feel, like the square root of 2, that's irrational. This is, it's obvious to us that the square root of 2 is not a fraction. And the proof is something that you can explain to everyone. I didn't get the same sensation for the quintic equation, the fifth degree equation. It was only years later that I got the same sort of sensation, and it was the same sort of level of obvious. And that was when I had more sort of mature, mathematical background. And in the end, it turned out to be a really naive idea, or some like simple idea that I could I could just visualize that picture, and then it was obvious to me that the quintic was not solvable. So if you have a quintic polynomial, it has some coefficients, 6 coefficients, and the idea is really to try to, like, what happens if you move the coefficients in a loop. So you start with one polynomial, you move the coefficients and go back to the same polynomial. And then you look at what happens with the solutions. So when you move it in the loop, the solutions will move continuously, but sometimes they get swapped around. Like the roots are the same, but the orders might switch. And for me, that was sort of the key point. Like, if you have a formula, let's see what happens if you like move the coefficients around in a loop. That's a very natural thing to think about. And then the steps really follow quite easily. Like, you see, okay, by moving around, you get some sort of way to switch the orders of the roots. And now you can play with this. Like, you can see that actually there are many ways to move around in a circle. And then you can actually get any permutation. And if you compare that to how like the square root or the cube root or the quintic root functions behave, you see that those functions are actually pretty simple. And they're too simple to, their behavior is a little bit too simple. So from that, you can basically sort of discover that there cannot be a solution. And when I realized you can sort of phrase it like that, it made sense to me. So it took, there was many years involved, but finally then I really learned why this was not possible. But I think there's some sort of takeaways here. So one is that in math, you can, many sciences can talk about truth. like, I mean, true statements. But in mathematics, there's this sort of I mean, you can really understand things. And for me, this is really why I really care about mathematics. You can really understand like every aspect of a problem, and it's just so precise what you can do. The other thing is that theory is actually pretty useful. Like, this is a quite concrete problem, but it turned out for me to be sort of useful to sort of just frame it in the correct way. So, you know, theory is important, but it's actually very useful. So I think this is sort of a difference between research level mathematics and sort of Olympiad style mathematics. So mathematicians, they have this like giant machine which is sort of designed to attack concrete problems, and they sort of work on polishing that machine. And that's what sort of makes it into a research field rather than sort of a competition. Yeah, so I guess one piece of advice would be to sort of be broad, like learn what you can learn from that machine. Like, try to be as broad as Kashiwara, like really know lots of subjects, so that if you don't succeed in this subject, then you can make progress over here. I had one or a few other pieces of advice. Actually, 4 pages with a. Actually, some of the pieces were mentioned by David. I also very much agree that mathematics is a human experience. Like, you really, I mean, collaboration really helps. Like, math is a difficult subject, and you can really learn a lot by collaborating and talking to other people. You can learn mathematics that you won't find in textbooks. The other thing is, I encourage you to travel. So most of you are starting university, and try to take advantage of that time to go places, like see new cultures, and you know, even if you'll just sort of really benefit from traveling, I think. And the last thing I wanted to say is, well, you guys have. You can basically become whatever you want. Like, you can choose in life what your job can be. And my sort of advice is to try to sort of avoid the temptation of like high-paying jobs or, I don't know, prestige. I think pursue what you really care about. Like passion is very valuable. So one thing that I'm very grateful for is that I'm able to work as a mathematician. So I could have maybe gone to the hedge fund industry or earned more money, but I'm really grateful for being able to, you know, spend most of my time doing what I'm very passionate about. So when you make your choices, try to, like, you know, follow your your passion. I think that's it's important. Okay, thanks. Oh yeah, yeah.
What do you do when you can't get a visual-oriented understanding of the subject? Do you think you should always try to get it?
That's a great question. So I work in a field called algebraic geometry. So there's some visual there's geometry, shapes and symmetries and stuff like that. But there's also algebra, and I really like the sort of interplay between these two. So when I'm not able to visualize, I can use algebra, which is sort of cold and unforgiving. So if you're working in something like 20-dimensional space that you cannot visualize, there's always algebra that you can sort of use to describe. So I have had the benefit of sort of using this interplay between these two fields, and I think that's very, very helpful. So. But yeah, in general, I try to think visually and then sort of translate it into mathematical proofs. And this only goes so well, but you sort of get intuition after a few years, and it's really helpful. Yeah.
More questions?
Yep.
Yes?
I was wondering, you think you also math besides school? And if yes, what did you exactly do? Did you, for example, compete, or did you join some classes or clubs? How does it look?
Yeah, I did compete in some Olympiads, and I was also very into programming and music. So I had sort of different interests in high school, but yeah, I don't know. That math was only. I mean, that was the real passion. Like that was sort of the artist experience of like. I mean, you really could go deep in mathematics. So yeah, but I think it was a lot of fun to compete in these competitions. Yeah.